Welcome to the next unit in the topic of thermochemistry, bond enthalpies. By the end of the unit, you should be able to know that bond forming releases energy and bond breaking requires energy. That the average bond enthalpy is the energy needed to break 1 mole of a bond in a gaseous molecule averaged over similar compounds. And you should also be able to calculate the enthalpy changes for known bond enthalpy values, which you'll get from your data booklet. Be able to sketch and evaluate potential energy profiles and determining whether reactants or products are more stable and if the reaction is exo or endothermic, and discuss bond strength in ozone relative to oxygen and the importance of the atmosphere. So going back to that particular case study we started off looking at structure and bonding. So bond enthalpy. What is bond enthalpy? Well, average bond enthalpy is the amount of energy required to break 1 mole of bonds in the gaseous state. And it's averaged across a range of compounds containing that particular bond. Now, from IGCSE, you should be aware that bond breaking is an endothermic process. It requires energy, and bond making is exothermic. It releases energy. If the overall reaction, therefore, is exothermic, the bonds have lost energy and more stable and have higher bond enthalpies. And conversely, if the reaction is endothermic, the bonds have gained energy and are less stable and have lower bond enthalpies. And that's essentially defining it in more equation terms. Okay, so in terms of using Hess's law, which we did in the last slide, and bond enthalpies to determine the enthalpy of reaction. So basically, we get delta H, or change in enthalpy, equals the sum of the bond enthalpies of the reactants minus the sum of the bond enthalpies of the products. Okay, so that's kind of touching on Hess's law, which we looked at in the last unit. In diagrammatic form. Okay, so basically what happens is the reactants, all the bonds have been broken, so you just form a series of atoms, okay, and they are then reconfigured into new products by the atoms being reconfigured and forming new bonds to form the products. So the enthalpy, or change in enthalpy, delta H, will basically be the sum of all the bond enthalpies of the reactants subtracted from the sum of the bond enthalpies of the products. Okay? And that will give you the enthalpy, or change in enthalpy of the reaction itself. So essentially, bond enthalpy calculations can be done basically from your data booklet. So the average bond enthalpies are in your data booklet. Okay, these are the examples for all the single bonds. Okay, so for example, the bromine-bromine single bond has a bond enthalpy of 193 kilojoules per mole, whereas something like the iodine-hydrogen bond is something like 298, or something like the sulfur-sulfur bond is 266 kilojoules per mole. So these numbers will be given to you in your data booklet, so you don't have to actually remember them, which would be slightly insane. So let's look at an example. Calculate the enthalpy change for the reaction. It's the Born-Haber process, so I'm teaching that with my 100 class, of nitrogen plus ammonia giving, nitrogen plus hydrogen giving ammonia. Okay. So you can use the data information in the previous slide, or use your own data booklet to find the associated bond enthalpies, and then come back and see if you've got the correct answer. Okay, so this is how it should have worked out for you. So the bond's broken. You've got a nitrogen-nitrogen triple bond in the elemental nitrogen, and you've got the hydrogen-hydrogen single bonds, but notice that you have 3 of them, so you multiply that number by 3. So it'll be 945 plus 3 times 435, which will be 1305, which will be a sum of 2,250 kilojoules per mole. That's the bonds broken. The bonds formed will be, okay, so you've basically got 3 NH bonds, which need to be formed. So it'll be 3 times 390, okay, and you've also got 2 of them, so you multiply that number by 2 to give 2,340 kilojoules per mole. So if you do the calculation of sum of reactants minus sum of the products, you'll get plus 2250 minus plus 2340, which will be negative 90 kilojoules per mole. So this process is, of course, exothermic. Okay. So just finishing off, going back to the example of ozone from structure and bonding. Ozone, as we now know, is decomposed more easily than oxygen, and the reasoning behind this is the associated bond enthalpies. Oxygen requires 490 kilojoules per mole to break, whereas ozone only requires 364 kilojoules per mole to break, due to essentially the bond order of the bond between the oxygens. Okay, this has a bond order of 2, whereas this has a bond order of only 1.5 due to the resonance. Okay, so this explains the reason why ozone is decomposed more easily than oxygen, because it requires less energy to break these bonds to form the free radicals, which we have already touched on in our structure and bonding unit. Okay, so if we look at the energy profile of this particular reaction of ozone decomposing to oxygen and this oxygen free radical, you will see that the ozone molecule is more stable than the oxygen molecule with the oxygen radical, because the overall reaction is endothermic. The bonds have gained energy and are therefore less stable, and therefore the product of oxygen and the oxygen free radical has lower bond enthalpies compared to those of the reactant.